We shall start. So what we have seen, we were talking about transportation problems. What we have seen an array type of representation called transportation array to represent the transportation problem. And we have also written down the constraint matrix. And we saw that the column below the variable xij is nothing but ei / ej. Okay. And we also saw that the basis matrix corresponding to a basis, so that has rank, I mean the matrix that has rank m plus n minus 1. So that we know, and deleting any row from the basis matrix or from a basis matrix, I should say. A basis matrix corresponds to a basis. There are many bases. Okay, so deleting any row will make it non-singular, that is invertible. That much we have seen. We'll talk about lower triangular basis, but before that, a little more understanding of the transportation array that we see. Okay, this one we are going to use. This is just a definition. A row or a column of a transportation array is called a line. Okay, so that will be frequently used. Now let us look at the first one. Consider a BTP, so balanced transportation problem. And when we are talking about BTP, I will understand that there are m number of sources and n number of sinks. So that is the standard thing. Now S be a set of some variables. What are the variables? Now variables, because it is m by n, variables start from x11 up to xmn. There are mn variables. So S be some collection, sub collection of these variables. That's okay. The moment you have selected a set of variables, so you can consider their columns from A and call that corresponding submatrix B. Okay. And also in the transportation array that you have, that table kind of thing. Okay. Whatever variables you have selected, you highlight those squares. So write down those variables, only the selected variables from S, and highlight them. Highlight these variables. Okay, that is what you do. So you have the matrix. From matrix A, you have selected some columns corresponding to the subset S, whatever xij are there. Corresponding to those xij, you have selected some columns. That is your matrix B. And corresponding to whatever variables are there, you select some those squares. Highlight those squares that are selected. That's what you do. How many elements are there in S? I don't know. Some elements are there. Okay. Now suppose that for I less than equal to m, I am trying to ask a question. Assume that the ith row of B is 0. So that matrix B that you have formed, that is 0. The ith row is 0. Now can the ith row of T is what? T is the transportation array, and then B is the submatrix of A. Now it is asking, can the ith row of T contain any highlighted variable? Well, the answer is no, because look, if you are looking at the ith row of T, what are the variables that you can see in the ith row of T? Now in the ith row of T, I can see a variable of the form xi star, that kind of xi1, xi2 up to xin, that kind of thing. And that, so, and what will be the column below xi star? Now that will have the form ei by, if it is xij, then it is ei by ej, so I will write a star. That style it will have. Okay. So in that case, look, ei by star, and this is a column. This is a column of B. But that cannot happen because you said the ith row of B is 0. Okay. So that basically means any variable xi star, okay, cannot be in S, given that ith row of B is 0. Okay. Similarly, the next question, suppose I is less than equal to n. Suppose that the m plus ith row of B, okay, m plus ith row of B is 0. Can the ith column of T contain any highlighted variable? The answer is no. Argument is similar. Okay. The next one, true or false. In that case, think similarly. The number of ones in the ith row of B, okay, here I can be anything. I can be less than equal to m, or I can represent anything from, like, anything starting from 1 to m plus n. There are these many rows. So the number of ones in the ith row of B equals the number of highlighted variables in the corresponding line of T. And this is true. Argument is similar only. Because the number of ones will tell, depending on what I you are choosing, I less than equal to m, or I or you are choosing I to represent like m plus 1 to m plus n, depending, or m plus ith, I less than equal to n, whatever. The first case or second case, it is the same thing. The number of ones would mean that that variable is there. Okay. So argument here is similar. This one is a little more, I mean, the next few are further observations. Number 4, suppose that the ith row of B has a 1 which corresponds to the variable xlk in A. That is, you had the A matrix like this, and you have selected some columns, and those columns constitute your matrix B. That is fine. And there in the ith row of B, you are seeing a 1 here, and it was actually corresponding to the variable xlk. Does this mean xlk belong to the set S? Now yes, xlk must have belonged to the set yes, otherwise how are you seeing that one here in definition? So by definition, otherwise that column would not have been there in B. So that is fine. So xlk is highlighted. Okay, fine. Now suppose I less than equal to m. This is number 5 I am talking. Suppose that I less than equal to m. A has 2 parts, remember? This first part is I less than equal to m, and the second part is I greater than m. Actually, it is like m plus 1 to m plus n. This is the second part. Okay. So This one sometimes we write as m plus I, no problem. Okay, suppose that I less than equal to m and the ith row of B has a 1 which corresponds to the variable, okay, xik. Because I less than equal to m, okay, now what will happen? Now if that means you are talking about a row of first m, and then the variable start from x11 up and go up to xmn, and here you will have the it will be something in that ith row, okay, and which corresponds to the variable xik, okay, because one can only be there in this thing. Remember the matrix has this kind of form. What is the first row? Now the first row will have some ones over here, then zeros. Here it will start from x11, x1n, and zeros. What does the second row look like? Now second row all zeros here, ones here. Okay, this is x21 up to x2n. These are the things. And the ith row will have in the ith place, one will appear in only xi1 to xin. These are the places it can appear. Okay. Does this mean xik appears highlighted in the corresponding line of T? Well, xik is there, and what is the corresponding line? I am not saying corresponding line of B. I am saying xik appears highlighted in the corresponding line of T. What is the corresponding line of T corresponding to this ith row of B? Now corresponding to ith row of B, the line of T is actually the ith row itself. A row, it will be a row itself, okay, and this row has the variables xi1, xi2, xi3 up to xin, and you would have written ai here. Remember, that is how you write. It is like xi1 up to xin, and then the summation is like this, total is ai, okay. Anyway, xik you have already highlighted, so it will appear in the corresponding line of, this is the line of T, so it will appear, no problem. Now suppose I is less than equal to n and you are looking at the m plus ith row of B, m plus ith row of B, okay, from here m plus ith row. Now if m plus ith row of B, to which line does it correspond to in T? Now it corresponds to the ith column of T. It will correspond to the ith column of T. Remember in the previous class I did like third row of A corresponds to this, seventh row of A corresponds to this. Okay. This will correspond to the ith column. Okay. That is what it will correspond to the ith column. And of course, before that, let me say something. Suppose that you are looking at the m plus ith row of B, and suppose that it has a 1, and that has a 1 corresponding to the variable xlk. I don't know what are L and what are K. I found that this m plus ith row, I am looking at B, okay, looking at B, and I found that m plus ith row has a 1, and this was corresponding to the variable xlk. Wait a minute. if I am looking at m plus ith row and I am seeing a 1 over here, if you have actually observed the transportation matrix, that the matrix, then the structure of this particular column should be, because at m plus ith row I have a 1, that means this is something and this is ei, because you are having a 1 at ith position, right? So it should be that. But below xlk you should be having x el ek, you should be having that. So that basically means you should actually have I equal to k. Okay, so that is what this question is asking, which correspond to a variable xlk. Then it basically means that k has to be I. Okay, so that is xli. It can only correspond to a variable of the form xli. L what I do not know, but it will correspond to a variable xli. That is what I am finding. Okay. Does that mean xlk appears highlighted in the corresponding line of T? Now yes, because the m plus ith row of B, that corresponds to the line, that is the ith column of T. And in the ith column of T, what are the variables are there? Now it will be x1 IE. Remember, that is the thing, right? This kind of a thing. This is like, this is for x1 1, x1 2. If you take I equal to 2, so what are the variables there? Now this will be x2 2, x3 2, that kind of. So what are the variables are there? Now x1 I, x2 I, xmi, these are the variables are there. So that is the line, and you have already highlighted xli. Xli is already highlighted. Okay, so it xlk, k is equal to I, appears highlighted in the corresponding line of T. Okay, after this observation we'll actually I did this observation because we are going to use them. You understand these things. Lower triangular definition I gave. Now let us have a small lemma that I am going to use for our next test. This is very interesting. This one says, assume that you have a matrix of the form like, I mean, it has k rows and k minus 1 columns. Okay, you have a matrix which has k rows and k minus 1 columns. Fine. Next, what? K is greater than equal to 2. Okay. Each column of y, this is the matrix y. Each column of y has a 1 somewhere and a minus 1 somewhere. Rest of the entries are 0. Fine. Each column has a 1 somewhere, a minus 1 somewhere, and other entries are 0. Each column. Okay. And it is also given that each row of y is a linear combination of the remaining rows. Okay. Each row of y is a linear combination of the remaining rows. Actually, that is yeah, that is not necessary, because from the first one, from A itself, what you know is that R1 plus R2, R1 being row 1 plus Rm is equal to 0. Therefore, the ith row is minus R1 minus this thing. So is a linear combination of the rest of the rows. So each row is a linear combination of the remaining rows. So that is maybe not necessary. It is following from this. And rank of y is k minus 1. That is given. Okay. So these are the two things given, A and C. Then there exist permutation matrices P and Q such that P, Y, Q is lower triangular. That's what it says. Okay. So this the proof will go by induction. For k equal to 2, that means you have two rows and you have 1 minus 1 or minus 1 1. Okay. And so this itself is lower triangular. Like you can take, so P, what do you take in that case? Now P will take 1 and Q you can take 1 0 0 1 identity matrix or anything. Okay, so that because that itself is lower triangular. So for k equal to 2, this is trivial. There is nothing to say. So now suppose k is greater than 2. So let k be greater than 2. Now what? Each column of y has two non-zero entries. Okay. And the rank of y is k minus 1. Okay. Now my question is, the following. Acha, before asking question, at certain places you, I mean, what helps is something like hope. Okay. What I was thinking, suppose somehow I could prove that, suppose somehow I could prove that y has a row with exactly one non-zero entry. Suppose y has a row. So then what I can do, I can take that one non-zero entry to the upper left column. I discussed how to do, like you can multiply by permutation matrices so that it would look like this. Then y would, with some permutation matrix p, y, q, it would look like 1, then some 0 0 0 0. Here you will have some star, I don't know, whatever is the column, and then you will have a big matrix X. That is what I will have. Maybe 1 or a minus 1, doesn't matter. It may be a plus minus 1, something like that. Exactly 1 non-zero entry, because y has 1 and minus 1. Okay, fine, no problem. Now what about X? Now look, in Y every column had two non-zero entries, 1 and minus 1. And on the top of X there is only 0 0 0 0 0. So therefore in X every column has 1 1 and 1 minus 1. Okay. And what about the rank of X? Now rank of X is 1 less than the rank of Y. Actually, there was a +1 you have taken away, so rank of X is 1 less, and X size is also 1 less. Okay. X size of X is k minus 1. The size of X is like k minus 1 cross k minus 2. Okay, that is the size of X. So therefore, the induction hypothesis is applicable to X. And so you will have some permutation matrix P dax X Q dax, and that is lower triangular. Lower triangular. And then in that case, what you do, you multiply 1 0 0 P dax P Y Q 1 0 0 Q dax. This is lower triangular because that is exactly this one. Okay, with one on the top. Okay, so this will be lower triangular. Now everything went with the hope to find a row with exactly one non-zero entry. Okay. Acha. Anyway, because maybe that is why I highlighted B. I kept, though it is following from A, but maybe that is why. So notice that each row of Y is a linear combination of the remaining rows. Okay. How many rows in Y are there? And there are K rows. Each row is a linear combination of the remaining. Naha. So then I delete one row randomly. Which row I want to delete? I delete rth row. So let YR be obtained from Y by deleting rth row. Fine. Okay. What will be the rank of YR? Now look, rth row was a combination of the remaining row that you have deleted. So rank will not decrease. Therefore, rank of YR will be the same as rank of Y only. So that means rank YR is K minus 1 only. That is, YR is invertible. It's a K minus 1 by K minus 1. There was only one row extra. So it's a square matrix. Rank is K minus 1. So find square matrix of size K minus 1. So it is invertible. Acha, theek hai. It is invertible. Now, because it is invertible, I now claim that the columns in YR, if you are looking at YR and looking at its columns, is it possible that each column has a 1 and a minus 1? No. If every column has exactly 1 1 minus 1, then the sum of each column will be 0. Then YR will be singular, because sum of the rows will be 0 in that case. if each column has a 1 and has a -1, then sum of each row, that is each column, will add up to 0. That means if you take the row sums, that is 1 1 1 multiplied by yr, that will be 0. So it basically means, and I already know that yr is non-singular, so this means there exists a column which has exactly 1, I mean either +1 or -1, I mean one non-zero entry. Let me put non-zero entry. Fine, no problem. Exactly 1, how did I conclude? Now if it has 0 number of non-zero entry, means the column will be 0. In that case, the matrix should be singular anyway. So 0 column is not possible. Every column having 2 non-zero entries is not possible, because in that case 1 will be 1 and 1 will be -1. So exactly 1 non-zero entry. There will be 1 column. So how many non-zero entries are there at best? And there are at best 2 into k minus 1 minus 1. That is at most these many non-zero entries. Okay. Now, can a row have can a row be completely 0? Now, no. Yr is non-singular. A row cannot be completely 0. Can every row have at least 2 non-zero entries? Now, no, that is not possible. By pigeonhole principle, there will be a row which has exactly 1 non-zero entry. So, which is what we wanted to show. Okay. So, therefore, the proof would be over. So, the detailed proof written over here, you can read them. Okay. So, why did we talk about this lemma? We talked about this lemma just to say that any basis is a lower triangular basis. Any basis of the BTP is a lower triangular basis. What does it mean? Now, if you pick a basis xi1 j1 up to, xim plus n minus 1 jm plus n, some m plus n minus 1 many variables, it is called a basis if the corresponding columns of A are linearly independent, that you already know. Okay. Now you form the basis matrix B by taking those columns of A. Okay. Now what does it look like? Now this one looks like, the matrix looks like of two parts. One is this source part, and then this one is the sink part. Okay, this is like row 1 to row m, and then the next one is row m plus 1 to row m plus n. No problem. Fine. Then here the claim is that there exist permutation matrices P and Q such that PBQ is lower triangular. Why not? What you do, you multiply. Remember what I said. What you do, you consider a matrix D that is created from B by keeping this one unchanged as such, and this one you multiply by -1, negative. So then the rank of B and rank of D will not change, because that's what I asked you in the previous class, that I have a matrix and my friend came in and selected few rows and made them like negative. Whatever was the written, he just wrote the negative of that. Whether the rank will change? You said the rank will not change. The rank will not change. Rank of B was m plus n minus 1. Therefore, rank of D will be m plus n minus 1. And in D, each column has 1, 1, 1, minus 1. Okay. So D is of the form in the previous lemma. Okay. Therefore, there exist permutation matrices such that PDQ is lower triangular. And if PDQ is lower triangular, then PBQ will be lower triangular, because there is almost no difference between the non-zero entries. I mean, the non-zero entries of B and D are at the same place. So that is how it is. And then you will ask this question. Now, I mean, what we will do with this lower triangular information? That suppose somebody said that I have this information. Any basis is a lower triangular basis. What will I do with this information? Now, with this information, you can develop a very important test to see whether a given set of m plus n minus 1 variables form a basis or they do not form a basis. Okay, so that is what we can do. Okay, so I will tell the this is fine, no problem. So this actually gives us a strike of procedure. That test, it gives us, it is a strike of procedure that it gives. I will tell that here. Acha. So what it says, suppose that you have a set of m plus n minus 1 variables. Now what you do, you highlight these variables in the transportation. I have written table, it is actually table or array, whatever, transportation array T. And then as usual, let B be the submatrix of A corresponding to S, means corresponding to the variables in S. Then the following are equivalent. S is a basis and the table T can be completely struck off by repeated application of the following rule. Find a line in T containing only one unstruck highlighted variable and strike that line off. Okay. Before I give the proof of this one, I will show you the example, what it says here. You remember that what it said? Find a line in the table, okay, that contains only one unstruck variable and strike that line off. And if you can finish up the table, then that is the next other equivalent statement. Then it is a basis. This is if and only if. Okay, let's say, suppose I have been given m equal to 3, n equal to 3, and I have selected 5 variables, x11, x12, x21, x23, x32. So I form the basis matrix. How do I form the basis matrix? Now for x11, I will write e1, e1. I know m equal to 3, n equal to 3, so it will be 3 by 3 size. Okay, this is e1, e1. x12 is e1, e2. x21 is e2 by e1. x23 is e2 by e3, and x32 is e3 by e2. I don't really have to write the whole big matrix A and then select the corresponding columns corresponding to this. Okay, so this is the basis matrix. And then what it is saying? Now then it is saying you highlight these variables. So I have only highlighted these variables: x11, x12, x21, x23, and x32. These are the variables I have highlighted. Okay. Suppose that B is a basis. If B is a basis, what did you tell in the proof of that lower triangular basis? Now there is a row in B which contains only 1, 1. B does not have 1 and minus 1, and it was D which had 1 and minus 1. B only has 2 ones. Okay. Anyway, so what you said, now there is a row in B that has exactly 1, 1. That should be found. So you find that. Now you have found fifth row. Okay, so you found fifth row, and then what you do now? Remember, this is how you proved that it is lower triangular. You deleted that. I mean, not deleted actually. You strike that off. Actually, we didn't strike that off. What we did, we took this one to the upper place. So actually, what happened? It is essentially this one was being located here, the rest of the zeros over here, and this thing, whatever is over here, that was appearing over here. And had I deleted that one and this, I would have got this one. Okay, this same thing. So instead of taking it to the upper left corner, I have just kept it here. But I remember, okay, this row and that column is essentially what I have targeted. Okay. Now what happens? Now which row does it correspond to? Which line does it correspond to in T? Now this is which line? This is the third line after this. So this will correspond to the third column. And because I have a 1 over here, remember my previous discussion. So this x23, whatever variable is there, that x23 must be available only here. So it says that this one corresponds to the fact that this third line, third column of T contains only one highlighted variable, and that is x23. And so it says you strike that off. Okay. After striking that off, what you have found? Now check for the, so what we did in the proof. Now we again tried to find one more row which had only one non-zero entry. So for example, this had 2, this had 2, this one. This one had 1, and this one also had 1. Okay, so I have selected this one, the second one. The second row corresponds to the second row of the table. Notice that the second row of the table has one unstruck variable. The x23 was there, but it was already striked. Okay, we already have struck it. Okay, so we found one more line containing one unstruck variable and strike that off. Okay, the whole procedure goes like that. Next one is I have found this one. This one corresponds to the next one, so that is the third line. Okay, and after that you find one row which has only one non-zero entry. You can either take the fourth row or the fifth row. I do not know what I have taken. I have taken the fourth row, and fourth row corresponds to the first column. Remember that? So first column, and then what is remaining is either you choose the first row or you choose the fifth row. any one you choose. Okay, so in that case, if you choose the so here I have what I have done. Yeah, like choose whichever. I have selected the first row. Okay, this line and this column. Okay, that is how you do. And the first row, of course, corresponds to the first row should have corresponded to the first line. This line is wrong. The first row should have corresponded to. So this is wrong. This should have been this. It should have been this. Okay. Had I selected this one, this picture would have been correct, because the fifth row corresponds to the second column. So this picture is for fifth row. This is for fifth row. Fifth row of this one. Okay, this is for fifth row. Okay, so what it says now, this is if and only if you can do, then you are done. Okay, if you cannot, then it is not a basis. That is what it says. For example, let me take one more over here. I will do it here. So here, let me write. So what is the, so I will write the matrix. Matrix is 1 0 0 1 0 0. That is x11. x12 is 1 0 0 0 1 0, and then x21 0 1 0, that is e2, and 1 0 0, x22 0 1 0 1 0 0 1 0, and x32 0 0 1 0 1 0. Okay, I don't know whether it is a basis or not right now. Okay, if it is a basis, then both these processes should finish and should finish by completely finishing this table and matrices. Okay, so I have highlight x11, x12, x21, x22, x32. Okay, in the matrix way, it says you should find a row that has exactly 1 1. Okay, you should find a row that has exactly 1 1. Can I find? Yes, there is a third row which has exactly 1 1. If you find that, strike it up and strike up that row and strike up that column. Fine. Then if it is a basis, you should find a row that has exactly 1 1. First row, no. Second, no. Third, no. Fourth, no. Fifth, no. Okay, not possible. I don't find a row with exactly 1 1. Equivalently, what it says, now you will find a line that contains exactly one highlighted variable. Here either you can choose row 3 or column 3. Choose. Suppose I choose column 3. Actually, if you have selected the row 3 with respect to the row 3, okay. By the way, uh, sorry. I am very sorry. I am getting troubled. Why I have written x32 does not appear there. You should have said this is x33's place. X32 x32 is here. Okay, so here what you found, now you found the third row. Similarly, you should find a line that contains exactly one highlighted variable. Yes, I have found a line, and this is this line, and this particular line actually corresponds to this line. The third row of the table corresponds to third row of B. That is it. Fine. After that, I should also find a line that contains exactly one unstruck highlighted variable, but I am unable to find that. So that is why it is not possible. Any line you take, row 1 or row 2, or any column you take, column 1, column 2, column 3, they either contain two variables, two unstruck variable or zero unstruck variable. So not possible. That's what it says. So going back to the theorem says the following. A set S is a basis if the table T can be completely struck off by repeated application of the rule. Rule is find a line containing only one unstruck highlighted variable and strike that line off. Okay. The proof is both the sides. The proof is very by induction only. So let's say A implies B. If you want to do that, suppose that you have S a basis. Now, because S is a basis, and let B be the basis matrix, I will go by induction. So the base case is trivial. So that is no problem. Okay. So take the basis matrix. Now, because you have already shown that in the basis matrix there is a row which contains exactly 1 1. Okay, there is a row that contains exactly 1 1. So what you do, you let b dax be obtained by deleting. So let's say let ith row of B contain exactly 1 1 at, let's say, some or let's say below xlk, the variable xlk. So whatever one you have, it is below the variable xlk. Okay, so let bdax be obtained by deleting that row and column from B. Okay, now because of our previous comparison that it contains a 1 at xlk, it basically means in the table also you will see a line in which xlk is the only one that is highlighted. Okay, that is done in the previous comparison. So you take, so then in T there is a line that contains exactly above, that contains the only highlighted variable xlk. Now delete that line or strike off that line. Okay, here you are also, do not say deleting, striking off, you say strike off that line. Now here is something that you have to observe, that BDAX you have obtained. Okay, see what you had, what was T? I mean, just wait for a moment and think, what was T? Now T was a transportation array. What did you do with T? Now I had only highlighted few variables, other variables I had not written. Okay, fine. After that, what did you do? Now I deleted a line. What do you mean by line? Now either a column or a row. But if you delete a row, column is also similar. Suppose you delete the last row. Just it is easy to understand. Suppose I delete. Earlier, what was, let's say now my transportation problem was M by N. M many sources, N many sinks. And then what you did, I deleted one row, last row. So the new transportation array TDAX, okay, is it not representing a BTP with M minus 1 sources and N sinks? It is. If you have deleted, if you delete a column, that would represent M number of sources and N minus 1 many sinks. So actually what is happening is that you would try to observe, and you will see that this BDAX is actually a basis for TDAX. Okay, and therefore by induction hypothesis, this TDAX, all the highlighted variables can be struck off. Okay, and hence we are done. Okay, a similar proof from B to A is also there. If you want to ask some question, you ask. You want to ask some questions? Okay, acha, before I even forget. So right now, what we have done, now we have discussed two types of tests for a basis. You have two ways to test. If I give you a set of variables and set up M plus N minus 1 variables and say you test for a basis, either you do the go the transportation array ways, find a line containing only containing exactly one highlighted variable, and go on striking off. If you can complete it, then it is a basis. Or you go the matrix way given by the lower triangular basis, that theorem. What? Now you find a row in B that contains exactly 1 1, delete that row and the column that where that 1 is appearing, and repeat. Okay, so if you can finish it in this way, then it is a basis. If you are stuck, if you cannot finish, then it is not a basis. There will be a third test that I will supply in the next class also. Are you asking anything? Are people here or not?
So we're here, but we'll have to go through it once the lecture or the notes again. Then we'll ask doubts.
So, acha, before I forget, every class, the first 5 or 10 minutes, you please feel free to ask. Okay, you at least ask something, whatever doubts you have. If you do not have, like, I would be anyway starting, but you feel free to stop me and ask your doubts. So everyone is free to do that. You can do that. Okay. So in the next class, it will be even more clear. Oh, sorry, that will be a few days, 3 days after this. That proof will be graph theoretic. So anyway, that will be that you will enjoy more. Okay, I shall stop here then.